Hello everyone, this will be the first online lecture for ME2761. Couple quick questions that everyone's been asking. So what about Memo 3? So I am going to move the due date for Memo 3 to the Friday after spring break. That gives you all a little more time to coordinate and get working on that. So note that I've moved that back to April 3rd. I haven't changed the due date on Canvas yet, but I will get on that. So I'm planning on doing no lectures on Wednesdays, so we'll just do one recorded lecture on Monday, and I'll just take whatever time I need on the Monday lecture, and then give you all a chance to work on the assignments throughout the week. For these team meetings, I need to do a little bit of work behind the scenes, but I think we should be able to get it set up so you all can meet on Zoom and have team meetings. I will send out instructions on that later in the week. If not, you can do it on Canvas, but it'd be nice if you guys had a platform for having teleconferences, basically. So I need to do a little research on that, and I'll let you know information about that. So we'll have this week to get that figured out, and then you guys can communicate via email for now too. Get coordinated for getting Memo 3 done. That pushes some of the other assignments back later. We'll talk about NX Quiz 3 next week. I've got to cover the lecture material for it today. And then NX Quiz 4 will be, as in schedule, will be the final on the schedule too. So we'll keep the NX assignments as is. I juggled the lectures around a little bit. We'll do the CDR presentations in class, on Mondays. I haven't quite figured out how I want to do those. We might do them as a big Zoom meeting. I might just have teams present to me via Zoom. I haven't quite figured that out, but we'll do those CDR presentations. I can't get you all in the same place, so what we can do is do a teleconference for that. It'd probably be too hard to get the whole class together on that, so at a minimum I'll have the teams use Zoom to work together and give the presentation just to me. So I need to work out the logistics of that. I'll let you all know. So I push that back a little bit, and we'll do those on the first, second. We'll do those on these weeks here. I need to give a lecture on computer-aided manufacturing. I might move that around a little bit too. As far as the project goes, I'm still talking to the department about that. I don't think we're going to be able to do the build because I don't think I can require students to come to the workshop. I think you can voluntarily come into the workshop and work on your project, but it's not something that I can require. So that means I can't require it across the whole class. So I need to think of that or think of a plan for that. So I'm going to take the rest of this week and spring break to come up with a good plan for projects. For now, don't buy any components because I highly doubt we'll be able to do a build. I just don't see any path forward on that. So it'll end up looking like some kind of a paper project with very detailed CAD models. I'm working on NX Access too. So this is the week for figuring out some details on that, and then also I've got spring break to work on details, so I'll let you all know more after spring break, and I'll be communicating via emails too. So if you have any questions, shoot me an email. Otherwise, we'll go ahead and get started here. So today I want to talk about finite element analysis. So what is finite element analysis? So you may have heard of this before. You may have been doing these before. If you're on a design team, I know a lot of our design teams do FEAs for parts. Something like this connecting rod here. If you wanted to know the stress in that, it's a fairly complicated shape, just regular beam loading, even regular like H-beam cross-section loading tables aren't going to work at these transition areas, and it's probably the transition areas where the thing's going to fail. So if we want to analyze the stress in complicated geometry, we need a method for doing that. And the underlying equations for stress are partial differential equations. So what we're really trying to do is solve a set of partial differential equations over some kind of an arbitrary set of geometry. So that's really what FEA is all about. FEA, finite element analysis, is a method of approximating the solution to differential equations, and specifically in this case partial differential equations for stress in this case. But it's not just stress. It could be thermal. It can be all sorts of other things too. So why do we use it? There's just a lot of things in nature that we can approximate as a continuum. So what that means is, if I have something like this connecting rod here, it's really made of a bunch of discrete little particles. You know, at some point in time, you get down to atoms and quarks and so on, and it becomes very discrete. It's all about quantum mechanics, which is way outside the scope of this class. But essentially, this is all just a whole bunch of little bitty things that are all connected together with forces. Sorry, you can probably hear my dog shaking his head in the background. But these little particles are all connected together with forces. But those particles are so small compared to the size of this connecting rod in this case that the fact that this is made up of a bunch of finite little particles doesn't really matter. We can approximate this as if it was a smooth, continuous changing set of parameters, and it does a pretty good approximation as long as we don't get too small. You know, for dealing with nanoscale things, this starts to not work because we're starting to get down to the size of the particles itself. But for things that are, you know, relatively large, continuum approximations work great, and we can derive equations for those continua, and then we can solve those using one of the different solution methods like FEA. And I mentioned this isn't just for stress. I mean, if you look at heat transfer, so you all are in or are going to have to take heat transfer. So this is the heat equation. It governs how heat would flow through a continuous body. It relates the change in energy to the change in temperature through a body in 3 dimensions. And it's a partial differential equation. In heat transfer, you learn how to solve this for some simple geometry, things like cylinders and plates and things like that. Well, it's good for learning the theory and you know, the basic way you solve those kind of problems. But for some kind of complicated geometry like this turbine here, you can't solve this equation on it because it's too hard to define the boundary conditions. And even if you could define the boundary conditions mathematically, coming up with an exact solution is for most geometries very unlikely or very impractical. So we want a way of approximating the solution to this partial differential equation over whatever geometry we like. Electromagnetics work too with finite element method. These are the Maxwell equations. If you want to predict the magnetic field in the air gap between a rotor and stator in an electric motor, the finite element method works for that. So you essentially approximate this geometry as a bunch of elements. So what is an element? I've been saying element a lot. Element's actually the edge here. So we model the behavior, and it's going to be easiest to talk about this in the context of stress. So we model the behavior of this component by breaking it into a whole bunch of little elements, those elements being the actual edges of this. So you can think about it like I'm taking this connecting rod and I'm breaking it down into a whole bunch of springs that are all connected together at nodes. So if you think about a tetrahedron, and I'm going to try to draw a tetrahedron. So if you think about, actually not a tetrahedron, let me split this in half this way, and now I've got a tetrahedron. But if you think about a tetrahedron, it's nodes, so in this case 4 nodes connected by edges. And if I have these nodes basically be points and then these edges be springs, and I put another tetrahedron next to that, I can stack up a whole bunch of those, and if they're small enough, I can approximate complicated geometry like this. So the trick is breaking this solid geometry into a whole bunch of little tetrahedrons that are really just springs connecting nodes together. And then find out what the effective stiffness of those springs, what would the stiffness of those springs have to be to model the like the Young's modulus, the modulus of elasticity of the material in question. So fluid mechanics, it's also, we can derive the governing equations for continuum fluid mechanics, so Navier-Stokes equations. We need to solve those too. In this case, finite element method doesn't actually work that well. We need finite volume method. So finite volume, instead of modeling something as edges, we essentially model it as a solid volume and derive and solve the equations over the volume instead of over the edges. And you think about in fluid flows, it's really not so much what happens at the edges that's important. It's more about the flow. So the finite volume method works better for that. So in theory, this is very, very complicated stuff. If you take the FEA grad level elective, you'll find it's probably not what you thought it was, because it's a lot of partial differential equations. It's not a lot of here's how you do this in in CAD software, best practices for doing it in CAD software. So that's mainly what I want to talk about today. Is a little bit about application and best practices. The theory itself is very complicated. It's really pretty gory behind the scenes. So by the end of today's lecture, you'll know a little bit about the application, how to use it, some pitfalls, different methods, but you really won't know, you'll know enough to be dangerous, let's say that. So specifically, we're going to talk about FEA for stress and deformation. It's an incredibly powerful tool. If you've done this before, you already know, but if you've not done a finite element analysis before, it's amazing. It allows you to solve for the stress and deformation in very complex geometry very easily. It's something that the average undergraduate engineer who sits in front of a computer with some tutorials can probably get decent results that are somewhat close to real world results with just a little bit of care in practice. Fluid dynamics is trying to solve fluid flow, especially something like this hypersonic fluid flow, is very difficult to get good results, especially for a novice. I did this professionally for a while, for 6 or 7 months, and it would take, for some problems, and I was doing low speed, low Mach number stuff, it'd take a month or two to get a good mesh. Just refining mesh in areas, doing mesh sensitivity studies. Just getting a good mesh takes a long time, and the solution times are long, and interpreting the results is difficult. There's all sorts of things with turbulence models that if you really have to understand the theory to get anything resembling good results out of it. I know some of our design teams do a lot of CFDs, I know the formula teams do, to varying amounts of success, and it's very hard to get really good accurate results with CFD unless you've spent a lot of time working on it. So it's really outside the context of this class too. That's more for the arrows. We do a little bit in fluids, but that's best to leave to people that are experts in that area. So we won't be talking about that. We'll just be talking about FEA. So basic process: define geometry. That's going to be a solid model of some kind. Define material properties. Create a finite element of mesh. Set up a boundary problem. Set up a solution. Solve it. Look at the pretty colorful pictures. So just running through these steps. So this is kind of a generic suspension link that I drew, not in very good detail. But you need geometry, so that's the first step. Define material properties. So for NX, it's got some material properties that are already in there. For a lot of things, you're probably going to have to create a new material property, put in things like Young's modulus, things like that. For linear systems, that's really all you need, but for nonlinear, it gets a lot more complicated than that. But for first pass, linear is not a bad assumption. I'll talk more about that later. But so in this case, I'm just picking aluminum 6061 and defining that to be the material. Now I need to mesh this thing. For arbitrary 3D geometry, a 3D tetrahedral mesh is pretty well the most common type of mesh, and so you can see these little tetrahedrons that this thing has been broken down to. As you can imagine, this is quite complicated behind the scenes. The algorithm for breaking arbitrary geometry down into a nice smooth little tetrahedron sets like this, it's pretty sophisticated. Thankfully you don't have to do that. NX has its own mesher, and most CAD programs have their own meshers. Dedicated finite element analysis software like ANSYS has its own mesher. So you usually just use the mesher, learn how to use the mesher. You don't have to actually worry about the gory programming behind the scenes. Okay, so this presents one of the most common opportunities for making mistakes, the mesh quality. So here I've done a mesh. How do I know if a mesh is sufficiently small and refined enough? So the only really good way to know is to do what's called a mesh sensitivity analysis. And so what you do is you mesh something with some size. So in this case, I picked some dimension like 1/8 of an inch, and it meshed it at that size. And it did a little bit of local refining in areas over here. And so more complicated geometry, it might make the mesh a little smaller. But it tries to guarantee there's no element larger than 1/8 of an inch or whatever that number was I picked when I first did the mesh. So I'm going to run this. I'm going to get a result on it. What I need to do is make the mesh smaller and see if the result changed. So ideally I would cut it in half, so down from 1/8 to 1/16, remesh it, rerun it. It's going to take longer to solve, and compare the results. And I keep doing that until my results stop changing at whatever level of precision that I'm looking for. That's very important. You're not done until you've done that. You're just going through this in one pass, unless you are extremely experienced and know just intuitively what size meshes are correct. Unless you put a lot of effort into it, you really can't trust these results until you've done a mesh sensitivity analysis. So it's incredibly important. Those of you that are doing this for design teams, run your results, make the mesh size half as big. It's going to take longer to solve. See if your numbers change. If they change, your mesh wasn't fine enough. There are some exceptions to that, or areas like over here where it's a really sharp corner. If you keep refining the mesh, you're probably going to end up seeing higher and higher spikes because you get to a little infinite stress concentration here because it's a sharp corner. Things like that. There's a little bit of filtering you might have to do with some results. So you kind of have to watch that. I've had issues where you continuously refine meshes, the peak stress keeps going up and up and up because of this corner here, which, if you cared about that corner and failing there, you wouldn't put a sharp corner there anyway. You learn more about that in machine design, by the way. But anyway, make your mesh. Boundary conditions. So we'll talk about the different kinds of FEA, but essentially for a static, nonlinear static, a linear static, which is what we're going to do for the NX quiz that's going to be coming up. You don't have to get too complicated with your boundary conditions. You essentially want to clamp onto the part and apply forces to it in a way that matches how forces would be applied to the part in the real world. So in this case, I put a fixed constraint on the inside bore of this, and then I applied a tension load over here. Now, in the real world, that's not exactly how it's going to be constrained. This would be a bearing constraint, and there'd be a bunch of other forces on this thing. So what I need to try to do if I'm doing a part by itself is do a free body diagram on paper and try to figure out to the best of your ability, figure out what are the forces, what is the best way to constrain this to make it as realistic to or as similar to the loading once it's fabricated up in a system. This is called a local finite element model, where we're looking at a part by itself. You can also do a global model where you have all of the parts in a mechanism connected with their kinematic constraints. That's pretty fancy. You can do that in NX. It's a little bit outside the scope of this class and this lecture. I'll show a video of what that looks like in a bit though. But that's going to be better at resolving what the actual stresses and constraints would be, but it takes more horsepower and more planning. And you kind of have to get this figured out before you start doing the global ones. Set up a solution. So we're going to use the NX Nastran solver. Nastran is a pretty old solver for finite element models. It's pretty reliable. We're going to be doing structural analysis. We're going to be doing static analysis, which means non-rotating, non-accelerating bodies. If you're going to do accelerating or rotating bodies, you need to do a transient analysis. We're going to be doing a linear analysis too, and where we assume the material properties are linear. So you all should remember when the stress versus strain graph, where it goes up, there's a linear case and it folds over and the material breaks here. And there was that region in the stress strain curve where it was linear. Linear FEA, we're operating in this range. So essentially linear is going to be fine up to yield for metals. As soon as you get to the yield, and you start to bend this curve over here, then linear doesn't work anymore. So, which in most cases is fine, because in most cases we don't want our parts to yield. If they yielded, they failed. But if you're doing something like a torque to yield bolt that's designed to yield, linear doesn't work because you actually want it to get into that yielded zone. Or if you wanted to simulate what was going to happen to something that did yield, linear is not going to work. So nonlinear is where you get to actually model this curve in detail. You need a lot more information on material properties. So in this case, we're doing a linear static. We're going to assume we're less than the yield strength. What's going to happen is your FEA program is going to derive a giant set of tetrahedrons in this case, figure out all the little spring rates for all these little components, and then it's going to derive the equations of motion for each of the nodes, essentially look at all the forces on each of the nodes, build a gigantic system of equations and unknowns, and then it's going to solve them. This matrix, this was called a sparse matrix. When you put it together, most of the elements in the A matrix are going to be 0. There are special ways of representing that in memory, so it doesn't take forever to solve. In this case, this is 82,400 or so equations and unknowns that it's got to solve. That's a big system. in compared to the stuff you do in classes, but for FEAs is actually pretty low. I mean, it's pretty easy to solve millions of equations and millions of unknowns on a desktop computer in a reasonable amount of time. Just solving that with like Gaussian elimination would take forever, like literally forever, like maybe the life of the universe for big systems type forever. So there's ways of reducing the solution time to reasonable amounts, thankfully. So there's lots of really good sparse solvers. You don't have to mess with that though, because usually that all happens behind the scene in the program you're using. So once it's solved, you can look at the results. So this is the deformation. Since it was fixed over here, there's no deformation. And then where I applied the force over here is where the peak deformation is going to be. You can see that this is 0.122 inches. So this part deflects about 1/8 of an inch. Stress. So if you look at stress, you can see this would be 3E4, so that would be 30,000. So that would be, this is in PSI, so that would be 30 KSI. And you can see the peak would be right there at that corner, at that stress concentration is where it looks like it's at. So this 6061 has a yield strength around 40 KSI, so this part wouldn't yield. It doesn't have a very high factor of safety though. So like a 1.33 factor of safety. So depending on the application, it's not very good. But this is at a corner, so I don't know if I trust this stress here. It might actually be higher because it is a local concentration. So I really want to refine that area and make sure that if there's any kind of a fillet in this, and like as this thing's going to be manufactured, this is probably not going to have sharp corners here. So if I really want to know what the stress is, I really need to model those fillets in there. I need to model the geometry as close as I possibly can and read a really good mesh in there to tell me what the actual stress is going to be in there. Because again, with just this by itself, it's not sufficient. You've got to know if your mesh is good enough for the kind of reliability and results you want. So for something like this, you might trust it and say, oh, this isn't going to break. But if the stress concentration is a little bit higher than this is a pretty big element here to try to resolve the stress in that corner. It might be significantly higher than that, and the part might fail, or certainly might have cracks start there. So it takes a little bit to interpret these results, but it's incredibly powerful. At least you can get the results. So it takes a little bit of work in refining them to get good results, but at least you can get them. Trying to do this by hand is just not an option. So that's a linear static, no accelerations or rotations. We assume the material behavior is linear. It's a good first approximation. If you need large deformations or yielding, it's not going to work. So you're going to have to do something nonlinear for that. But it's a good starting point for a lot of analysis. So here's a linear static of a bike frame. Now you see animations like this. This is just a sort of a pseudo animation of the stress. It's going to solve the deformation at steady state. This is just showing that animation as it goes from the unloaded. It just basically ramps the force up from the unloaded to the loaded configuration. So you got to watch your animations. It's not this actual deformation too. Usually, like this deformation here, visually is exaggerated quite a lot. A deformation here would be exaggerated quite a lot too. So you got to watch that. It's not going to deform as much as it shows unless you put the scale on the deformation to 1. And then you probably wouldn't even be able to see it deflect, actually. One comment on this and why this is so powerful. If you look at the stresses in this bike frame, you see it's red up here and it gets red in this area down here at these joints. But you can see some of these tubes, like this area here, never gets away from being that light blue. That's the minimum value. If you were trying to make this thing as light as possible, you really want to remove material here. Ideally, if your load case is correct, and you don't have any other weird load cases to worry about, ideally you want the whole thing to be the same color. That means it's evenly loaded. So things like this back here, basically not really getting stressed at all. Maybe you could make those lighter. Areas here, maybe you need to beef those up a little bit. And ideally, if your load case is correct, you want it to be as consistent in color as possible. There's actually some tools for helping do this automatically called topology optimization, where you basically start with a big block of material and run it into a iterative algorithm that will do an FEA, and then it will automatically remove material and then keep refining the structure and doing FEAs until it's consistent within targets for factor of safety. I've seen some parts made using that, and it's really pretty interesting. Some students did that for a Formula Electric project and made some brackets, and very interesting organic shapes came out of that. So that's kind of neat. That's kind of fun. nonlinear static. So if you need to model yielding, you need nonlinear. So still no accelerations or rotations. It still needs to get into static equilibrium, but we can model nonlinear material behavior. You need more information about the material to do it, not just the modulus of elasticity. Transient. So if I want to model accelerating or rotating bodies, it's transient. I have to model things over time. These are inherently take longer because I'm not just solving at a time step. I'm solving over lots of time steps potentially. So it takes longer to solve. I can do one part. I can do multiple parts. One part would be a local. Multiple parts would be a global. This is a global transient finite element analysis of an engine. So it's got all the kinematic constraints in there. It's modeling all the stress. Looks like it's even modeling gas forces in there because you can see this stress in these bores. So really good model here, right? This is really going to tell you the stress in these components about as good as you're ever going to get, depending on your mesh. So when you can even see things like these connecting rods, how they turn red. So really, yeah, that's really powerful. It takes a long time to get these set up right, but it's definitely solvable on a modern desktop and just take a little time. Nonlinear transient. So nonlinear transient, you start getting into really fun stuff like large scale deformation, modeling, yielding, and buckling and things like that. You start getting into needing dedicated software for that. LS-DYNA is sort of the big program in nonlinear transient world, in the nonlinear transient FEA world. So when you talk about crashing cars and software, it's almost always LS-DYNA, which we have the solver for NX. I had never done it before, so I have no idea where to even get started setting this up. But some really interesting stuff in the industry. So this is from Tesla. This is them crashing their cars in nonlinear transient FEA. They're even modeling the airbags deformation in this. Really neat stuff. I would be surprised if this was not done in LS-DYNA. I'm guessing it was. GM, when I was an intern there back in 2003, they were doing the same stuff in LS-DYNA back then. They had a car that they had crashed, and then they had reproduced the crash in LS-DYNA, and they had a video of the car's frame buckling next to the car that had actually been crashed, the physical car. And it was amazing how accurate the model was at predicting buckling of this really complicated deformation and buckling. And I'm assuming it's only gotten better in the last 17 years or so. Here's another video from Tesla showing a pull impact. And you can imagine how this helps you as a design engineer. You don't have to crash a car to figure this out. You can crash it in a computer, and I mean, computer power is cheap nowadays. So something like this, in the grand scheme of things, doesn't take that long to solve. With a fully parametric CAD model, too, you can just change a few parameters, update the model, and redo the simulation. And you could actually have it sweep through a whole set of different parameters and run through a whole matrix of different cases and just spit the numbers out for you on what's the best configuration. So really powerful, interesting stuff. So that's a little bit on FEA. So what we'll do in NX Quiz 3, and you saw that in the schedule. Let me go back to the schedule. We're looking at, it'll be April 10th for NX Quiz 3. So I will post lecture slides for that on Monday when we get back from spring break. I need to get you all access to NX. It's doable. I'm able to get it at home. It's going to require some IT help though, because I think there's already VPN problems and you have to VPN to use NX. If for whatever reason we can't get NX to work for everybody, there's another option. We'd have to switch to a different program. But there is a program that's just available for free for all students, and I've installed it and it works. So we'll pivot to that if we have to. I would prefer not. It's not SolidWorks for those of you that are getting excited about SolidWorks. But so we'll see. I prefer everyone to be able to use NX, but there's some IT problems that have to get solved. So I will let you all know. I'll try to get that all figured out this week, but if not, I might use next week, spring break too, to get that figured out, and I'll give you information. If we need to push these NX quizzes back, I'm happy to push them back just to make sure you guys have access to them. So that's it for today. So I will not have another lecture on Wednesday, but I will communicate via email and try to get you all some information on how you can have team meetings using Zoom or some other kind of meeting software on Friday. So campus got an extended license for Zoom that you all should be able to use. I need to do a little bit of work on that, a little bit of background before I and make sure it tests and all works before I want to commit to it though. So I'll let you all know. So that's it for today, and I will see you next week, or at least you guys will see me next week. Thank you.